So we are going to go ahead and start on the back of your notes section where we left off. We had talked about LD30 a couple days ago, or LD50, sorry, and safe concentration. So we are on the second to last page, and we're going to start with the Toxic Substance Control Act, okay? So this gave the EPA, remember this is Environmental Protection Agency, it's the U.S. governing body, the authority to regulate a lot of chemicals, okay? But it doesn't include food, cosmetics, and pesticides. Anyone know what regulates food? That would be the FDA, the Food and Drug Administration. So this is the Toxic Substance Control Act, okay? It allows us to regulate these chemicals. Under the Toxic Substance Control Act, nearly 85,000 chemicals are registered, 7,700 are reported actively in use at quantities higher than 25,000 pounds per year, okay? And then 200 chemicals have been assessed by toxicity testing, and then to date, only 5 chemicals have been restricted or banned. So out of these 85,000, only 5 have been restricted or banned. And, you know, one of those is probably the thalidomide, right, that we talked about, okay? And also DDT, right? Although it says it doesn't give it authority to regulate pesticides, but DDT would be an example of one that's been banned. So we also have the Federal Insecticide, Fungicide, Rodenticide Act, FIFRA, and this is a law. It says that manufacturers have to demonstrate that a pesticide will not cause unreasonable adverse effects on the environment, right? So after we saw that DDT was super harmful to the bird populations, Congress said, well, hey, we should probably have a law that makes people test all of these pesticides before they actually go into the environment. So they have to demonstrate that the pesticide will not cause adverse effects, okay? So let's talk about these studies that they do, these toxin studies, okay? So what are some problems? Well, they're not conducted on humans, right? It's unethical to say, hey, we're going to test this drug and we don't know what it's going to do. And it's conducted on a few species, right, like rats, and then we just say, oh, well, it might happen like this in humans because it happened like this in a rat, but we aren't 100% sure. The other problem is we have synergistic interactions. Syn means together, so synergistic interactions means that when we have two risks put together, they end up causing more harm than the risks themselves alone. Okay, so it magnifies the risk if we have two chemicals together. What's a good example? Well, for example, the health impacts of asbestos, remember we said asbestos is found in walls, they are much higher if an individual also smokes tobacco. So with asbestos, we said that there was a high likelihood of them developing respiratory disease, and that is increased, not just doubled if they smoke tobacco, but increased, you know, tenfold or something that's even a higher magnitude. Okay, so if individuals do 2 of these actions, it might have a much, much, much higher risk than if you were to just add up the interactions themselves. So when we talk about toxins, okay, we can have different toxin concentrations, and these toxin concentrations depend on a variety of different factors. So we looked yesterday at the birds, right? The birds, the eagles at the top of the food chain with DDT. Well, what impacts whether or not a chemical is going to be super toxic or if it's going to accumulate? Got a variety of different things. So the first one is solubility. And from chemistry, you might know soluble means can it dissolve, right? And that's the same definition we have here, how well a chemical can dissolve. If it's soluble in water, then it has the ability to be washed into aquatic ecosystems or groundwater, right? So, for example, like vitamin B and C, those are water soluble, so you pee those out. Okay, so those can go into aquatic ecosystems. They're oftentimes going to be found in our wastewater, and so these are some of the things that our wastewater treatment plants have to try to get out. Then we have solubility in oils or fat soluble, right? And these are found a lot of times in soils, okay? They're also found in animal tissues, okay? Now, vitamins in humans are fat soluble, are D, E, K, and A. Now, do you need to know which vitamins are fat and water soluble? No. I'm just providing a reference to explain that some things are soluble in water, some are soluble in fat. And this should make sense because you may have remembered talking about polar and nonpolar substances in chemistry, right? And so it makes sense that polar dissolves in polar, like dissolves like, and nonpolar dissolves in nonpolar. So typically, the things that we're going to be worried about are going to be the ones that are fat soluble, right? The things that are going to be stored in animal tissue because those are going to build up in the system, and that's where we talked about bioaccumulation yesterday. Persistence, you guys read about persistent and non-persistent chemicals. This is how long a chemical stays in the environment, right? Like its half-life. We talked about a half-life is the amount of time it takes for something to get to half, right? And we talked about that with isotopes, right? With carbon decay. So eventually over time, these chemicals are going to break down. So for example, this insecticide has a half-life of 1 day, meaning it only takes 1 day to break down. Radon, 4 days. Okay, then we get to other things like Roundup, herbicide that we've talked about, 7 to 70 days in water. Atrazine, this is an herbicide that was banned, 224 days. PCBs, okay, or DDT, we're talking 30 years, right? So even after we ban DDT, it can still be found in soil. So the persistence really plays a large impact in how deadly these chemicals are. All right, organism size and age, right? This is a terrible picture, somebody drinking alcohol, pregnant, with a cigarette, right? Smaller or younger organisms are more vulnerable. We talked yesterday about teratogens, right? And those are those types of chemicals or substances that cause birth defects. So with teratogens, the reason they cause birth defects is because they have a much larger impact on smaller organisms. Think about how many cells an organism has if it's a baby. Not as many. So it's going to be a lot more toxic to an organism that's a lot smaller than it is to an organism that's larger. We have a lot more cells that can store and process and metabolize all these toxins, whereas a fetus or a smaller organism has less. So why exactly are children more susceptible than adults? So there's a variety of reasons. First of all, children are more susceptible to toxins than adults because they have a smaller body size. So the toxins are going to be concentrated in their body, right? So you see it's more concentrated here. They have a bigger body, so it's going to be more dispersed. And you can, if you run out of room, there's only 3 things here, you can write that on the next page too. They have a larger skin surface area compared to their body weight. So they have children, right? Children weigh less, but they still have a lot of surface area, meaning a lot of area where those toxins can seep in if they're going to be able to get in through their skin. Adults have a much larger body weight, right, mass, but they still have a pretty decent amount of surface area, okay? Also, children have less developed immune systems and detoxification systems. They haven't been exposed to as many things. So you can see over here some other factors. Their breathing rate is increased, right? So they're breathing more often. So if there's an air pollutant, right, they are going to breathe it in more often. They consume more food and water, right? So if it's foodborne illness, because they're growing. Spend more time on the ground where there's nasty stuff. Their skin is more permeable and their organs are still developing. Okay, so all of these are reasons why children are more susceptible than adults. All right, last but not least, we're going over bioaccumulation and biomagnification. These two you absolutely 100% need to study. Put a star next to them. They appear on every single AP exam I've ever read. Okay? Bioaccumulation. This is accumulation of chemicals in one organism. Circle, underline, highlight, star, one organism over time. Okay? So for example, if I'm a fish, as I grow throughout my lifetime, I get more and more toxins because I'm eating more and more zooplankton that are contaminated. Okay? Comes from small exposures that build up over time. Those chemicals end up getting stored in the animal's tissues. So for example, mercury, this is what happens with fish. So fish eat organisms that have mercury. Over time, those fish end up accumulating more and more mercury because they're eating all of these contaminated organisms that have mercury in them. Remember I said accumulate. The word accumulates in there. It accumulates in one organism. Then we have biomagnification. Biomagnification is an increase in chemical concentration as the chemical moves up the food chain. It's being magnified. Okay, magnified. Again, we can also put mercury in fish here. Okay, because fish are eating lots of smaller fish that have mercury, and humans eat fish, and humans accumulate mercury, right? So for example, here the mayfly is eating toxic pollutants. The bluegill eats lots of mayflies, so it gets even more. The bass gets even more, and the human's eating the bass, so the human has the most. So I put that little picture down there. I'll show you in a minute, but you have that picture to remind you in your note packet the difference between bioaccumulation and biomagnification. Okay, bioaccumulation is in one organism, biomagnification is in a food chain. Okay, so again, you know, phytoplankton absorb PCBs, the zooplankton eat it, then the herring, the salmon, the mammals, and it builds up and up and up. And we saw that with DDT as well. Okay, and this is the nice little diagram that I have for you, right, that is in your sheet. All right, so you're going to be looking at LD50 today. Remember, that's the lethal dose that causes 50% of the organisms to die. So what you're going to get is you're going to get a packet, okay? And remember we talked about dose response curves, the graphs that have a curve like this. In order to find LD50, you look at the graph where it says 50% of the organisms die, right? And then you just draw a line down and you figure out what that dose is, okay? Remember, the safe concentration is found by dividing it by 10. It walks you through this, okay? You're going to create a couple graphs. Remember, with graphs, things we have to remember. You have to remember we need even increments. Count by 2s, count by 4s, count by 5s, 5, 10, 15, 20. You can't just write the numbers, okay? We need a label on both sides of the graph. Label here, label here. All right. Title, okay? So you're going to have percent and the number of deaths, okay? Or sorry, the dose and the death rate, okay? All right, and then you're going to fill in a chart, okay, on lethal dose. And then the last thing you're going to do is you're going to look at the lethal doses. You're going to use an orange sheet, and you're going to look at different substances and their LD50s. Okay, so when you're done, hand that in. If you have extra free time, work on your review. We will be working on the review tomorrow. Your test is on Friday.